Good morning, good afternoon, good evening, depending upon where you're joining us from. I'm Ira Feldman. I'm the Executive Director of Maptec, and I would like to welcome you to today's Maptec IMAP Semiconductor Industry Speaker Series. So welcome, and we're glad you're here. In terms of future events, please plan to join us next week for the Road to Chiplets Heterogeneous Integration Testability on March 15th and 16th from 8 to 11 a.m. Pacific time. You can find more information on the website, maptec.org. Please register. It's a free event, courtesy of our sponsors, and we're looking at the challenges of testing advanced packaging and what has to be done in structuring that packaging so that it can be tested, so that it can be economical. It should be a very interesting discussion. In terms of Maptec, we are a membership-supported organization which helps pay the bills, so we can do things like this free webinar and our free events. So please consider joining if you haven't already, or renewing at maptec.org. Or if your company is interested in sponsoring, we have many levels of corporate sponsoring. So please contact Betty or myself, and we will certainly help you join in support of Maptec. And it is my great pleasure to introduce Professor Santosh Kurinec from the Rochester Institute of Technology. She will be speaking on Microelectronic Engineering Education at Rochester Institute of Technology, a model for workforce development for the semiconductor industry. Professor Kurinec is a professor of electrical and microelectronic engineering at RIT. She is involved in the IEEE and the New York Academy of Sciences. She has a very distinguished academic career, including multiple internships and sabbaticals at semiconductor companies. And her research focus is advanced integrated circuit materials and photovoltaics. And with that, I welcome Santosh.
Hi, good afternoon from here in the East Coast, but good morning in the West Coast. I'm Santosh Kurinec, as Ira introduced myself. And the topic today I've chosen is very much in need for our current needs of developing workforce. So therefore, I'm going to talk about the microelectronic engineering education that has been developed at RIT as a model for workforce development for the industry. So I belong to the Department of Electrical and Microelectronic Engineering at RIT. So I'm very happy to partner with MTech on this presentation, and I think that our message will go around very well. So the outline of my talk, I'll just give basic introduction to myself and technology as such, and the technology trends which we are going to see now, and what are the grand challenges and demands for our industry to go forward, especially in terms of keeping manufacturing in-house and workforce demand, and how we are addressing that in our education. So I will go through my slides, and if you have any connections, as Ira mentioned, please ask me the questions whenever you would like to. So give you a brief introduction to my journey here. It's just to let you know that we all go through our own journey, and it's good to share with others, because this is what we want to tell our young students, to be very optimistic about their journeys. So I had early interest in math and science that brought me to physics curriculum in University of Delhi. So I did my BS, MS, and PhD in University of Delhi. And my PhD was in National Physical Laboratory in New Delhi. NPL is something like NIST of United States. It maintains the standards, and that's where we learned about maintaining standards for electrical testing. So I worked on magnetic ceramics, and later on polysilicon for low quality solar cells, low cost solar cells. And that brought me to photovoltaics, and that's how I came to University of Florida in the Department of Material Science and Engineering, where I did my postdoc. So learning at UF about materials analysis and also improving solar cell efficiencies. And that was the time that technology was moving to polysilicon gate for CMOS. So that is how I came into CMOS technology. And I joined the Florida State University College of Engineering and worked on porous silicon and polygate. And then I found that RIT was developing CMOS for education and research. So I came to Rochester despite the fact that there was a lot of snow there, but I got used to driving in snow. I also did my sabbatical at IBM Watson Research Center. And this way it gives you perspective of academia and industry, and also national boundaries and global boundaries. We learned how to address that. So with that, my introduction. So I will just tell you about the broad spectrum of semiconductor chip application. Of course, you are in Maptec arena, you know all that microelectronic chips are almost finding applications in all aspects of our life, from energy, from defense, from space, from competition, internet, and everything, communications. So therefore, we have chips almost everywhere in all applications. So demand for chips is going up, and therefore the production will go up, and therefore we need people to do those things. And this is a graph we made on the technologies that enable this by semiconductor chips. So start of the internet, when ARPANET was formed way back in 1969, that was the foundation. And after that, we grew to growing worldwide. World Wide Web was invented, and then we got all the search engines, e-commerce, social networking, cryptocurrencies, Internet of Things, artificial intelligence, now immersive experience, and we are all the way going to quantum computing. All these developments that have taken place in last 4 or 5 decades are enabled by the semiconductor chip. So that is the heartland of all what we see today. And this is the SIA picture, which I really like from SEMI. It says that without these people, we will not have the chip, and without chip, we will not have all that. So that means ultimately it comes down to how do we make the future engineers who are going to make the future devices for our future needs. So just a quick supply chain issue here. How chips are made. Chips are made from, if you ask anybody, say young kids, do they know that chips are made out of material that comes from sand? So basically, supply chain goes all the way from sand to packaged chips. So silicon is extracted from sand by Siemens process, and then a crystal is grown using Czochralski crystal growth method. So that is also a big supply chain issue. Who is growing the crystals that we need for semiconductor chips? So a single crystal of silicon has diamond crystal structure that gives us semiconductor properties, and it's a very good semiconductor with a band gap of 1.12 eV. And that is how we make them wafers out of these ingots. The ingot size has gone up. These days, wafers have 300 millimeter, and in the future, we may go to 450 millimeter wafers. So that means we'll have to grow bigger crystals. And once you have big crystal, then you have to find ways to cut them with the diamond wire sawing to make wafers. Then we actually use our circuit. The circuits are designed. The basic switch is a MOS transistor, which turns on or off. When the gate voltage is applied, transistor turns on, so current flows between source to drain. So that is the switch. And that switch can be connected in inverter characteristic, gates, and circuits. And then we make the chip design here. So the entire chip design is made. It's converted into masks. So for each layer, masks are actually fabricated on chrome glass plates. And then we use photolithography to print the circuit on the chip. And with a stepper and scanner, you can make many dies on a wafer surface. So this is how it shows that how photoresist blocks implantation. So you can implant some regions of silicon to make them more conducting than the others. And finally, the process goes on and on and on, all the steps. Then we cut the die out, and then we package that on a packaging. And then a final chip is made, and then chip is planted into circuits. So all this manufacturing happens in foundries. We call them foundries. This is a global foundry clean room. And all the processes are very computer controlled, but process engineers monitor the processes. So this becomes a very complex technology. That's what we teach from the bottom up to our students. Moore's law, as we all know, that the number of transistors is increasing, doubling every year, every 2 years. And you see here the Moore's law, which we know that everyone says that it's going to end and it's going to end, but we always find new innovations to keep going with more chips on the more transistor on a chip, and therefore more performance, more functions. And so simple here is a CMOS circuit shown here, which is planar CMOS. It has become now FinFETs. And we have seen that how the innovations have taken place over time. in scaling geometrically, equivalent scaling, and going from planar to FinFETs. So remarkable improvements have happened in photolithography. Of course, we are trying to print smaller and smaller features, and also in materials and processes and designs. So we go from silicon to strained silicon to high-K metal gates to FinFETs. These are materials innovations, and then photolithography innovations have taken us to smaller and smaller size. So if I really sum up since 2005 to today, we went from planar CMOS to FinFETs, and we are going to nano wires, vertical nano wires, nano sheets, nano ribbons. We will go, as you see there, all this trend here in terms of the geometry. In terms of the interconnect, we started with aluminum. We went to aluminum, copper, tungsten wires on the back end of the process. And now people are looking for cobalt lining, graphene or carbon nanotubes, and optical interconnects. In dielectrics, we went from plain silicon dioxide to high-K dielectric material and different types of gates, from metal to polygate, back to metal gates. So that shows you that inventions and innovations have happened all along to make this happen, because there's a willpower to get better transistor and more transistor on a chip. With that trend, that's why educational programs becomes complicated too, that we have to include that in our education. Intel announced just recently their roadmap to Angstrom era. They call it Angstrom era. So it seems that the scaling will continue to go on with time as we move on to smaller and smaller technology nodes. And performance per watt is also improving. We are performing more at a less energy cost. So that's also very important in designing your chips. Back on the line now, once we make the front end of the line, this is your smallest cabin. Just think about a multi-story building here. This is your smallest room. I call it the transistor with the channel length here. But all these transistors, there are billions of them, and they have to be connected with wires. So all the wiring is done in multiple level here, as shown here. This is a cross-section. This is actual SCM image, which cross-sectional image of a chip at the back end of the process. This is a three-dimensional view of the wiring. And you see that the wires are very small, and the distances between wires is very small. But as you go up, the wires becomes big. And this is because the high power lines are more toward the surface in this drawing. So this is what is the back end of the process requires. So it has been enabled by going from aluminum to copper, electroplating, chemical, mechanical planarization. You have to planarize after every level, align the next level, and keep going to 10 levels or 15 levels. But in the end, you have to solder bump, because that is going to be connecting to your package. But this is also being considered to be replaced by optical interconnects. So then you will put optical layer here. There'll be photodiode modulator and a waveguide. So this way you can have optical interconnects between chiplets and chips. So this copper lining has changed from, now they are trying to go for cobalt lining right in the vias here. So that you can get a good barrier for copper so that it doesn't destroy the silicon properties and other. So what we see in this small building, just imagine that the resistivity changes by 21 orders of magnitude. Imagine in such a small volume, the resistivity changes by 21 orders of magnitude. This is an amazing marvel of technology, really. So then we go to heterogeneous integration. Of course, we make CMOS chip, which is mainly computational chip. We want to integrate with memory. We want to integrate with silicon photonics, sensors, bio devices, or optical detectors, thermal sensors. So then we have a sort of different types of performance and different types of purposes of these chips. So we want to connect them together. And that's why we go to heterogeneous integration. So the roadmap for that is, as we're going forward, from 2D integration to 2.5D to 3D integration. And that has been enabled in drilling holes into silicon, these transposers. They have vias called through silicon vias, and they are able to connect chips through the connection through them. And that's also a big innovation in the 3D integration. So that's the next step that we have to learn on the future integration schemes as the chips becomes more and more dense. Now, coming back to the CMOS baseline process, which is used for computational CPU units, we have seen that over the time, the technology node has become more advanced, 25 nanometers to 18 to 13 to 12. And the players, you see all the companies which were involved at 25 nanometer node, but as the node is shrinking, the number of companies is also shrinking, or they are agglomerating, or they are consolidating their resources. And at the very high technology node, something like 3 nanometer or beyond 3 nanometer, only 3 main players are left in the world. And this shows that some of the small companies which were using larger diameter, so larger nanotechnology nanometer node, eventually sort of stayed in their business, or only those which could go to smaller technology node, they sort of consolidated. So this trend has resulted into many things that we see now. Many of our students were hired by companies like Cypress, Sony, Infineon, or Texas Instrument. And now many of those foundries have gone abroad. And therefore, we are left with smaller companies in our backyard to hire the students. Just yesterday, I got this news that Apple just announced M1 Ultra chip. So it's a very specially packaged 2 M1 chips, which is giving, they say, the best performance ever. And I think it's a 3 nanometer node, and it has 114 billion transistors on a chip. And this will be up to 128 gigabytes of high bandwidth and low latency memory device. So this shows that the performance is really increasing as we are talking about today. So this is the trend that's taking us forward. So let's look at the International Roadmap for Devices and Systems. It's called IRDS roadmap. We used to have National Technology Roadmap for Semiconductors, NTRS or ITRS, but now it is IRDS. And if you look here from 2022, but at present to 2034, how the transistors are changing. They're changing from fins to multiple fins to ribbons and nanowires. Now the question is, how and who will go from here to there? So who would be the engineers who will be working on 2030 nanometer, in 2030 or 2040? So they are probably in high school or they are in college. They have to learn all these to get there. So every time I talk to IRDS or I talk to SRC or even to Maptec, I will tell them that when we make the technology roadmap, we should also make an educational roadmap. What do we need for people to know to do things which we say we are going to do? So that's really important for us. In addition to all the CMOS technology I was talking about, the semiconductors are having a lot of applications as a discrete or power devices for power transmission, high-speed rails, for light industry, electric vehicles, power supplies. And so therefore, there are devices like bipolar transistors, MOSFETs, or insulated gate bipolar transistors. So even these devices are forming a lot of applications. They may not need small technology node, but they may need more information and knowledge about these areas. So this is growing. Same thing in solar cells. We are putting rooftop solar panels everywhere, but solar panels also have to improve in efficiency and reliability. And they also follow the same process as semiconductors do. They go from sand to silicon ingot growth, wafering, and then making panels. So we have to put inverters here. We want to know more about inverters. We want to improve the metallization of solar cells. This silver is causing a lot of cost in solar cell. Can we replace silver by copper? Or will they lie reliable for 25 years on a rooftop? So a lot of semiconductor knowledge goes here as well. If you look at the standard foundry semiconductor industry, these are the jobs for engineers, starting from fab manager to production manager to maintenance manager. So I'm just talking about, and this particular drawing was made by Quirk and Serda. I'm just referring to their drawing. And it really shows you that at some point in year 2000, we could hire associate degree students or technology students, BS and MS students, and they were working in all these fabs. So as the technology is becoming more complex and more involved, more education needed. So this arrow is sort of sinking a little bit. You see that here. So we may need more MS and BS students here in the middle heartland of the foundry. I took the data from TSMC. TSMC has about 65% students are BS and MS students who work in these fabs. So we need to produce the next generation of these engineers from bottom up to the top.
Did you, sorry to interrupt, did you just say 65%? So there's
65% workforce is BS and masters.
Oh, okay.
Yeah, education-wise. Yeah, that's the data I got from TSMC, yes. Thank you. So now let's look at the situation we have in the US right now. So I made this map and I just hope I can explain you this way. This is where the United States is, and we have been last for 4 decades. We have seen that we have imported a lot of talent from outside. So a lot of talent came from outside to US universities, which are very strong in research and development. And there's a motivation for these students to come to US because we have a very good university system. And once they come here, they do master's or PhD, they get hired by the industry, they get hired by the academic positions or research directors. And then we are also outsourcing a lot of our jobs outside. So this cycle is going on, but what we are missing is this bridge. So domestic students who do BS in domestic institutions, they have dollars of loans to pay. So they will not go for a master's or PhD. And therefore, the whole industrial complex, this bridge becomes very weak. Do we send a lot of students to US high-tech industry? Because that industry is also outsourcing. So therefore, now if we want to bring manufacturing back, we need to make sure that we strengthen this bridge. We strengthen our students, we teach them in such a way that they can be immediate contributors to the industry. Whether they come from community colleges, or they come from small universities, which have to educate them well and be very productive members of our technology sector. So that's
a question, sorry, but
yeah.
Back to, is there any organization or government and government body that knows these numbers that talk about this flow? I mean, so we can hear people's journeys as you talked about, but has anybody studied this numerically and said how big is this problem?
Now they are noticing that. I will show you some data, but I got some data from labor statistics, and also I've been also talking to IEEE for many years. But what happens is that in 2004, when a lot of foundries started to get outsourced, and we saw the decline in the employment of semiconductor industry. When you see the decline, then motivation for kids to go into the programs goes down. So there is a lag between supply and demand. I understand that, but at the same time, I don't think we are communicating very well to K through 12 educators that where the jobs are going to be. And I think that is what is important. And I'm making that case everywhere I go to, you know. So especially all these consortia. And now we are looking into that. And I myself came from outside, so I can understand that. I came from University of Delhi to US as a postdoc. So, but we want to get foreign people to come with us as I came. But I also started to notice that over time, the motivation for domestic students to go for PhD has gone down. And the reason for that is, one of the reasons is that US education is expensive compared to international BS degree. So there are a lot of factors which are responsible. And also you should have an industry next door. When I come from Rochester now, Kodak was a huge company in Rochester, New York, and Kodak employed 55,000 people in Rochester, New York. But when Kodak shrank, a lot of population sort of dispersed, and now some small startup companies are coming back, which hopefully bring good results. So
thank you.
It's multiple factor questions, and if you see the history of outsourcing, I've seen myself that we outsourced the furniture industry, we outsourced the appliance industry, we outsourced display industry, televisions, electronics over time. And as you keep on outsourcing, you also have skill extinction in those areas. But we also improved skills in internet and also in use of the chips for other applications. So it goes both ways. Thank you. The BS program in Microelectronic Engineering at RIT started in 1982. So way back, and we are celebrating 40 years of our celebration in April 2022. The program started when PC revolution just began. So that was the beginning of, oh, now a PC is coming to be the mainstream things people would need. It was the person of the year in Time magazine at that time. So Dr. Fuller, our pioneer visionary department head, he started this program. It was inaugurated by Nobel laureate Jack Kilby from Texas Instruments in 1986. So since then, we kept growing our clean room facility for teaching. This is the entrance to clean room. This is the surrounding buildings. We made some more areas around our main building. So we have class 10,000 for teaching, in fact, class 15,000 now square foot of clean room. So this is how our clean room looks like. And I will refer you to this website. Please, you can go to this website and click on all these bullets and see what kind of tools we have. And this is a very student-centric facility where students can go in. We give them chemical training, safety training, so they can work in the clean rooms. And we have 150 millimeter, 6-inch diameter silicon foundry for CMOS and MEMS processes. We have optical lithography, I-line and G-line. We have ASML stepper that we use for G-line. We have in-house mask making capability. You can draw the circuit and make the mask. And then, of course, we have all other CVD, PVD deposition, etching, ion implantation for doping, and all the wet chemical process, wire sawing and wire bonding, and then 3-5 semiconductors for other types of devices like power devices and multi-junction solar cells, those kind of facilities we have. And so that's our clean room that has developed up until now. We would like industry help to improve our clean room, put some more materials, more supplies, and more test facilities in our clean room. Our BS program is something very different from any other schools. So this is what I call it as a model for education. We have built-in co-op programs. It's a 5-year semester program. Students go for co-op after second year. So after second year, they take 6 months training in the industry. Come back to school, go back to co-op, come back to school, go back to co-op. So they do at least 1 year of co-op training in the industry. So we have 100% placement of our students in the industry. And all these light blue courses are microelectronic related courses. Then we have electrical engineering courses, electives, and also basic physics, math, calculus, chemistry, and general ed. What is flagship of our program is this 1 year of capstone design project where students actually do research. So this is unique here. Another thing you might have noticed that these 2 courses, statistics and design of experiment and IC technology, they do in second year, sophomores, and then go for co-op. So they're ready to do design of experiment with the industry because they know how to use jump software. They know how to do the process control when you have multiple variables. So these are our fab-centric courses, IC technology. We make full metal gate PMOS here after second year. Statistics design of experiment. And thin film, we teach students how to deposit films and etch them. Photolithography, 2 courses on photochemistry, optics, and sublithography and extreme ultraviolet lithography. CMOS Factory class, they run the whole factory in the class. And then integration of modern devices and the senior project. So this is called the bottom-up spiral. Freshmen come here, they do a full fab here, and then they go for co-op. Then do modern device physics, process integration, go for co-op. And then come back, do factory lab and do research, and they graduate with 1 year of co-op experience and 1 year of research experience. So in 5 years, they have 1 year of research experience and 1 year of co-op experience. This is the lab they do after second year. So starting from the design, they sit down and design the chip, CAD design, they understand the design rules, they make the whole layout, and they do the process flow. So this is the process flow. I can't explain in a short amount of time, but this is the process flow. They go through, they build devices, and they test them. They simulate them and test them using our test lab. This is done in 1 semester, 14 weeks of classes, and 1 lab per week. So in 14 sessions, they complete the whole process from design to test. So this shows you their flow. So this is all the processes that go in 1 semester class, and they learn to use all these tools. Then CMOS Factory is more advanced class. Here they run the full CMOS process, NMOS, PMOS with polygate, and it's a quarter micron CMOS technology. They use work in progress tracking system, Silvaco simulation system, statistical process control, test and quality management, and they do a factory model. They put all the information on the factory model and they run the processes and test in the end. This is how they know how a foundry works. So over time, in 1982, the BS program started, and then we started Master of Engineering. The IBM had needs for that. Then we started Master of Science, then joint BS, MS program and PhD. And over time, we've gone from 3-inch to 6-inch wafers, and we are making all kinds of devices now in our lab, whether it is IGBT or magnetic tunnel junctions or tunnel devices and ferroelectric devices. So we have a platform to build novel devices. That's what we offer. What kind of jobs are there for our students? They can be hired as design engineers, VLSI design, analog design, new devices design, and the knowledge areas are listed on the right-hand side. They can be device engineers. They can actually make a device in the sense what kind of materials to use in the devices, what is the function of the device as such, what the IV characteristic of the device will be. So they can be process engineers, they can be test engineers, yield enhancement, pattern specialists, and business and policy advisors also, and educators too. So we are using all these areas where we are sending our students. So I'll refer to the Maptec article, which was written in 2002. I'm so happy that this article was written at that time, and it got a lot of visibility. And at that time, in 2002, I wrote, this is a valuable resource for the semiconductor industry. In fact, it has been. And now, 20 years later, we are still saying the same thing because now the demand is coming up. And that's why I reached out to Maptec. Okay, let's update this article and tell you what we are doing right now. And we are celebrating 40 years of a program. This is the website. Please join and register for this conference. Our students will be presenting on April 8th next month. So Maptec Vision, when I see the Maptec Vision mission, I think that we have a lot of things common and some things we can develop in the future. So Maptec dedicates to improve and elevate roles of assembly and test professional in the industry, which is very important. We want to bring that as well. And therefore, packaging and assembly is an important area for us to grow. So I've talking to College of Applied Science and Technology. They have a good packaging center, and we would like to have some cooperative program with them. And I think Maptec can connect us with the industry there. So we can set up some special program for the packaging side of this technology. So I think that will be something to look forward to. The impact that our program has had. So if you do the pyramid, it's called the pyramid of all the semiconductor companies, from design to simulations to making instruments, and then the companies that design the chips and companies that make the chips. So in this pyramid, we have placed students almost everywhere. We have 1,500 graduates placed in the industry. And the stars show that all my students who work in these areas, all these companies they work on. So they've gone to major graduate schools as well. Our alumni have gone to worldwide in Japan, Korea, Taiwan, and Singapore, even some in Australia and India and Europe across the US. So which tells that we have had a very good impact of our program towards the industry. But now the question is how to increase the volume so we can provide more. We stay very active with IEEE, and we are also very much connected with the career fair with the industry. So industry is welcome to join us on career fairs and look for students. Now comes the problem. This is the data I got from US Bureau of Labor, that all employees in the semiconductor industry over time, in 1994, we had this trend, but there was a sudden decline around this. So this sharp decline by the semiconductor industry to hire engineers is very, very, you have to think about it, why it happened and how it happened, because we started outsourcing most of the manufacturing. And if you look at our enrollment, this is the enrollment to our program. When PC Revolution became, we had very high enrollment. But over time, enrollment had a roller coaster approach because that was the dot-com boom. Many, many young kids went to the internet attractive jobs. And then there was some ups and downs based on the supply and demand situations. And around year 2000, US announced National Technology Nanotechnology Initiative, NNIN. So we had some balance here, but then this decline follows that decline. So now everybody's concerned that we have shortage of workforce in the semiconductor industry. So how do we bring this back up again? So that's what we are trying to talk to all the universities and educational institutes all across. What can we do to bring it up? Because we are seeing a lot of fabs coming up back to our region. So US outsourcing physical electronics, biofocus, and social media emergence caused all this decline over time. Now, Intel announces new microchip plant in Ohio following the similar in Arizona. So we are having these fabs coming up. They are already digging and building. So what can we do to supply these many engineers? They say that there'll be 3,000 high-paying jobs and 15,000 additional indirect jobs in the community. So we are looking at how to create that workforce. Maricopa Community College and Intel, they have announced an enrollment joint program called Quick Start. So these are the programs that we need to start and connect with the local community. So semiconductor skill shortage is the problem today. They say that because the demand is going to go up, industry is going to $600 billion industry, and chip manufacturers have announced huge investments. So new fabs are being built, and we will need so many workers as by 2025. There's no way we can think of producing them in such a short amount of time. So we are looking into what's immediately we can do so that next couple of years, you can send the engineers to these new fabs. So that's where we need help from the government, from the industry, from, I think, all sources, educators, communities, that how can we bring semiconductor education to our K through 12 and onwards. So what we are doing is, we are getting students from K through 12. So we have to encourage math and physical sciences in high schools. So students come as freshmen to our program, or they can come through community college transfer students. They can go to 2 years community college, doesn't cost as much. And then they come to our program, go for co-op and back. And we'll supply engineers through co-op as well as full-time jobs for industry, national labs, graduate schools, and academia. So that is what we need to, these are rate limiting factors are in red. These are rate limiting factors right now. So demand is there, but these are the rate limiting factors. So we need to get more input of students. So what are we doing to create domestic workforce? One model I suggest is we can get students from community college after second year. So let's say I go to Portland, Oregon, or I go to Arizona, go to community college in Boise or in Texas. Okay, after 2 years, transfer to our program, go for half-year co-op, half-year school, co-op school, earn while you learn and graduate. So that's one model of getting more students train them for the industry. So it's shown here. If we go with community college transfer, we'll give you engineering 3 years. If we go to undergraduate student, we'll give you 2 to 5 years. We can give you internship students and full graduates. PhD, we'll give you in 4 to 6 years. So this is what we need. We need the trained student for future technology nodes. We need students to do heterogeneous integration, improve the energy efficiency of processes, and work on power electronics, photovoltaics, bio, and MEMS. So all this requires this kind of knowledge. So that's where we need to have a joint venture and help from each other. So give me an example of a transfer student, Jesse Judd. He agreed that I should share his information with him. He transferred to RIT from Monroe Community College in 2015 and graduated in 2018. And he worked with Silicon Labs. Then he worked and has a co-op experience. First internship he did at RPI. The second internship he did with AMD and then in NXP. And then he got hired as an engineer in NXP. So he became a well-established engineer in NXP. Brian Novak, he transferred from Hudson Valley Community College in 2013, and he graduated with BS in 2017 and did master's while working for Northrop Grumman. Northrop Grumman has a lot of demand for students these days. And so we provided that and we're providing them more. So what is needed to sustain and grow? The rapid pace of innovation that characterizes the semiconductor industry is fueled by influx of new ideas and new participants. So most of the participants, as you've seen, that people are retiring now. The average age of a person in the industry has gone up. So current skills will retire and we need to create new skills. So we need to increase visibility. We need to provide incentives to students, grow faculty. We have shortage of faculty who can teach processing courses. So where do we find them? We have to look for them. Continue and maintain state-of-the-art laboratories, modernize your tools, test and metrology and technical stuff. We need more support from the industry. Give us money so that we can invest in training students through best. Give us more tools so that we can train them on high quality tool sets. Increase government support, incentive for students, scholarship and research grants. So I would say that this is the tree that even in order for a tree to grow, you have to feed the fertilizer. The fertilizer comes from faculty, students, staff, resources, infrastructure. That's where investment should go to, where rubber meets the road. And I think everything will follow after that. So that is what we are telling. That's how we formed American Semiconductor Academy, ASA. In fact, I would connect Maptec to ASA. ASA is a consortium of universities and industry who are related to semiconductor microelectronics, and they are moving together to this mission. So they are working with the government and industry, a joint venture to accelerate the, to maintain US competitiveness for national security, a nationwide education training network of US semiconductor workforce and accelerated commercialization of innovations. So we also want to make that happen. So that's one way the Maptec can also connect with the ASA. We are part of the ASA also. And so keeping in touch with our alums. So our program is very dedicated to make sure that our students are happy wherever they are and they are well connected and valued what they're doing. So I often, whenever I go visit my industry for research and other discussions, we meet our students. My students in Portland, Oregon, Phoenix, Arizona, in IMEC in Belgium, we place some students there, NAM Lab in Germany and Minneapolis, Minnesota. So they are contributing everywhere. There are a lot of them in Austin, Texas. So they are contributing very aggressively, heavily, and valuably to the industry. So with that, I will say that we keep in touch with our alumni, and some of them have become very big innovators. Tim Tobin established a company, and here 2 of my alums are working in US Patent Office. They look at the patents because they understand the technology, so they can learn the patents very well. And we always welcome them to visit us in our facility here and suggest us what we can do to improve our labs because they have more experience now in the industry. So with that, I will say that my special acknowledgement to Maptec for inviting me, to Ira, thank you so much, and to Razina for doing all these arrangements. And of course, I commend my faculty who teach microelectronic courses, and they have combined about more than 200 years of experience of teaching this in the labs, so which is great. And my department and also our industrial supportees, people who support from the industrial affiliate program, and our alums all across the world. So I think I went very fast because I was aware of the time that you may have, but I'll be open to any questions you may have, and either now or even later, you can send me the questions. Thank you very much. And
thank you, Santosh. So yes, we do have a bunch of questions. Well, one was a comment is that ASA is working with SEMI, which is a Semiconductor Equipment Manufacturing Association. So there is some industry involvement that a lot of us are involved in through SEMI versus Maptec, but maybe Maptec should certainly look at that a little further. So a bunch of questions I think you've touched upon, and One is, as we're moving to heterogeneous integration products, the packaging is really the enabling technology. And, the diversity and the quantity of chiplets is going to increase. The packaging is really critical to this. And as you touched upon, but, when you listed the jobs, didn't seem anybody going into packaging engineering. When you talked about the fab activities, you didn't really talk about packaging. So how present is packaging in your program, and if it's as low as I suspect it is, how do we individually or through our companies, or how to change that? Because I think packaging technology is really key to where we're going.
Yeah, you're very right. And I agree with you. I'm a material scientist myself, and I'll be more interested in developing the back-end processing technologies for the future. The reason for that is actually for the last many years, as I mentioned, most of the packaging was done outside. Like we know that most of the packaging are run in Malaysia or in Thailand or some other countries. And therefore, when you don't see a job next door, that's what happens. So I think that I've been telling my department that we should have a packaging elective course for now. We can start with a professional elective for students to take, and then they can also do internship in a packaging company. And then we'll bridge with the College of Applied Science and Technology. They have a packaging tool set that I'm starting to use that. We also have photonic packaging right now, fiber optics combined with. So there's some work at the research level at the undergraduate curriculum. I think you're very right. We need to develop a course begin with. So recently, one of my students did Masters of Science thesis on packaging overall. And the moment he finished his graduate study, he got hired by Intel. So there is demand for that. So I will certainly bring it to my faculty to make sure that we can include. But again, coming back to any university, when it wants to expand, there has to be a influx of students, because now the university would say that, okay, you're getting so many students, let's have new faculty and let's have a new lab and let's do that. But certainly, I think I'm going to make a case to our the dean, and that we should look into a packaging-based program, which is going to happen. It seems like that. Mm-hmm. So we'll certainly focus on that.
Good, and that's good to hear. A few slides back, I think you said there's an estimated need between 70 and 90,000 semiconductor workers, but additional in 2025. I'm assuming that's not all new fabs, but also includes retirement and
yes,
things like that. But what do you have a feel for how much of that is, let's say, engineers and architects and designers versus people operating the equipment in the factory?
Yes, actually, you're right. Very correct. I have reached out to SEMI and SIA and also labor statistics that give me the statistics. Even we are having a meeting day after tomorrow with ASA. I'm asking them, I need the full data. How many are the technicians you need? How many the process engineers you need? How many construction workers you need? So I think this number, as we get from different sources, and as an educator myself, I don't think I can analyze that much data, but we are told that the ASA is told that there will be need for such a huge number of engineers to work for the coming fabs. So even if it's 5,000, even if it's 10,000, it's a lot. If you're only graduating 20, 30 students in my program. So therefore, I'm talking to other universities that send students to us, and we can expand the facilities. We can help other universities or other small colleges to do some of the training. We can train technicians and engineers. We often do short courses for industry. They come here for a week. In 1 week, we teach them how to build the full MOS transistor, So we will need something like that. So that's the whole idea of my coming to this conference, is that if we send out this information, that we can do that. And if there's a demand, then there will be resources. So universities want money, they want tuition dollars. So they want more students, then they expand the facilities, they hire more faculty and things like that. Mm-hmm.
Okay. And what, for your different level programs, I mean, what what is the background of the students? Is it just an interest in STEM? I mean, you take freshmen out of high school as long as they're interested in STEM. Is there any other real requirements for the programs?
Yeah, we bring them for a tour of our lab. We tell them about our technology, and if they're interested, they apply for it. And so I'll send you another video from one of my students and how he got into this program. Maybe you can share that with your community.
Okay.
So it's I would say that this interest comes from the K through 12, and once they come to see our facility, then they get interested. So if they don't see it, they may not know it. So that is why I feel that our high school education is not yet bridged very well with the needs of the industry. So for example, how many students in high school know what semiconductors are? How many of them know what's inside their cell phone, how they're built? So we need
zero unless their parents work in the semiconductor industry.
Yeah. And there is also in popular culture also doesn't talk about it, So compared to when, say, 20, 30 years ago, when I used to watch TV, I used to watch shows like MacGyver and all, they used to, I used to be intrigued by how things are made, So I think there should be some more exposure to young students that these are really, I mean, come to think of it, it's a marvel of technology, how these chips, such nanometer scale, billions of transistors, they never fail, your chip always works. And that's amazing technology. I think kids should be happy to be part of it. Yeah.
There's a few people who would like to reach out to you. You can either, if you want to give out your email address verbally, which will be in the recording, or if you want to put, Rosina can put it in the chat. It depends whether you want it on YouTube or not. So,
yeah, RIT, I think I have my email on the first page.
Okay, so perfect.
I will welcome to give a tour of our facility.
Okay.
You're welcome to join us, see us here, and also work with the industry, some ideas about capstone projects. So I'm seeing some here.
And then the other one, I think, as you touched upon, that somebody's asking it anonymously, but they're a graduate student. But I think, either institutionally or maybe at an individual level, they could somehow leverage the offerings of what you have. So
yes, that's a very good question, and please feel free to contact us. And I'm also talking to ASA. We should find a way that you can come spend a semester with us, run through the fab, and something like that we can do. Yes.
Instead of a semester abroad, a semester in Rochester, right?
Yes. Yeah. I mean, if you come in the fall semester, you will see nice weather from fall to winter. And if you come in spring, you will see nice weather too. I mean,
good. All good.
There is also a question, one more question I see is materials characterization and failure analysis. It's a very good question. We do some materials analysis using, of course, scanning electron microscope, scanning tunneling microscope, and also TEM. And we do some electrical test, but we still have to improve our lab for, which is called accelerated failure tests. Something like that we need to develop. And that's where we need some facilities to come here. But we can do cross-sectional analysis of the device and also the electrical analysis of the device. For accelerated test, we have to develop some tools.
Well, beyond doing the work, I think, having a curriculum tied to that, because having talked to failure analysis engineers, test is hard enough.
Yeah.
Failure analysis is even harder.
That's true.
And so learning the theory and the practicality of how to do it, I think would be a very valuable curriculum, because you talked about the billions of transistors that don't fail. It's because people have spent a lot of time on the few that do to try to keep them from doing that.
Yeah, that's true. I think the failure analysis is a very important topic, and we can develop courses on that. If we can get, I went to see AMD failure analysis tool. I wish I had this tool here. So, but that's something that we can also look for a course that some industry can teach as a failure analysis course. That's how the new ideas we have to develop. I mean, okay, so we can have a special course which we can develop with the help of industry.
Great. Rosina did put your email address in the chat. It is on the title slide. So I thank you very much for an excellent presentation. Thank you, Santosh. Look forward to finding other opportunities to engage, because education is such an important topic, and it's foundational. If we don't have people who know how to do things, things fall apart or we can't move forward. So it's very, very important. So thank you very much.
Thank you very much for this opportunity. I really enjoyed it, and feel free to stay connected with me, and I'll connect you to my other faculty as well. And also I'll let my institute know and ASA know about it. Thank you very much. Thank you for having me.
Perfect. Thank you. So just a reminder, next week on March 15th and 16th will be the next Road to Chiplets, focused on heterogeneous integration testability. It's a free event, so you can register today at maptec.org. Look forward to having everybody join us from 8 to 11 a.m. Pacific. And with that, I wish everybody a good rest of your day. Thank you for joining us. We will announce some additional semiconductor industry speaker series, webinars, and we will post the slides and the link to the video on our website, maptec.org, next week. So thank you, everyone, and I wish you a good rest of your day.